Right. So let me just bring up the chat. All right. So today we're going to talk about graph theory, and graphs are used in many real-world problems, from maps and navigations to modeling human relationships in a social network to I don't know, like to modeling like a lot of like even marketing. I mean, it's used almost everywhere, and you can utilize graphs as a tool in order for you to like not hack your way through, but rather like, you know, enhance the way how you solve certain problems. So from genetic algorithms to many other things. It really goes in many fields. Yeah, I mean, even we use it sometimes in game dev, so that's for sure. So let's talk about that. So let's try to dissect it just a little bit. Usually, like, so let's say, so we can actually like start this by saying a graph G, okay, consists of a set of vertices. It's not called vertices or anything. It's like a vertex is the singular, vertices is the plural. So a set of vertices V and a set of edges which we usually refer to as E, where each edge is a pair of two vertices, okay, where each edge is a pair of two vertices, so two vertices V and W, okay, and where also V and W, they actually belong to the set V, all right? So they are in that set of vertices. They are not outside of that set. So if you define a list of vertices and you have a list of edges, you define a graph. And these V and Ws, so like the vertex 1, vertex 2, they are not outside of that array. Like, so they're not like something that is outside of the data structures. Is actually important to mention here. It's also worth mentioning that in some books, if you are actually like, if you look in many other reference books, sometimes edges are referred, I think I'm writing it correctly, referred to as arcs. Okay, so sometimes you will read this in a book, it says like an arc instead of an edge. Also, so this is like, this is one of the like other naming. In some cases, edges carry additional information and this additional information is called like such as weight. So let me just add a little space here. So such as weight. Okay, so it can have a value. So for example, like an edge could look like that. So an actual graph, it depending on what graph you are dealing with. So it can be like something like this. Okay, this is, for example, a graph. And as you can see here, every vertex has every edge has a set of two vertices. So this is V, for example, and this is W. So if you have 1, 2, 3, 4, 5, so you have, let's say, 5 vertices, and you have 1, 2, 3, 4, 5 edges. Okay, and every vertex has, and every edge has at most two vertices. And here you can have a weight, so it can have a weight, let's say like 4, 10, 11, 16, or 0. Heck, it can even be -3, right? So it really depends on what kind of weights you put. This is basically what a graph is all about, right? Today we're not going to discuss algorithms per se, but we're going to discuss what are the graphs and their what are their types, and what problems and what questions we usually ask in order to resolve certain problems with graphs. Okay, so that's the objective of today's lesson. And it's very, very important to really like understand this. So once you learn the algorithms, you will immediately know, aha, I'm using that algorithm in order to solve X problem, and so on and so forth. Okay. All right. So this is what a graph is in general. It's coming from I think discrete math field, or it's actually a mathematical field, by the way. It's like a field in mathematics, studying graphs and their properties. We are studying a subset of that. We're not studying the whole thing. There are many, like it's a huge world in there. And it has been like being explored, like I think since the 1800s or 1700s. I really cannot recall right now. By mathematicians. So it's been explored by mathematicians since a very long time. Okay, so let's talk about types of graphs. So let me change the color here. So I'm going to call this types of graphs. Okay, so types of graphs. Let's see. I would like to keep it like in order. So let's talk about this one. So this one you're going to see for sure. It's called undirected graph. Let me actually write it in a different color here. So I'm just going to write it undirected. Undirected graph. And an undirected graph is just simply like it's a type of a graph. So it's a type of a graph that don't have a specific direction, that their edges where, okay, let me write it this better. So a type of graph where edges don't have a specific direction. Okay. And it's actually quite simple. It is the same thing as I already have drawn to you. This is, for example, is an undirected graph, and usually people think of it like this. So, i.e., a set, an edge, which is so an edge E, for example, or edge of VW is identical to WV. Okay, so this is what a what an undirected graph is. So an undirected graph will be something like you have vertex 1 connected to vertex 2, connected to vertex 3, and this one's are two connected. And for example, this is connected to vertex 4. This is undirected graph, no directions whatsoever. A directed graph is the opposite of this. So you have directed graphs. Is practically speaking, so a directed graph, by the way, sometimes they call it, sometimes it's called, sometimes called a diagraph. Okay, so just an FYI, so you might actually hear this terminology even more. So a directed graph is a simply like has edges. I forgot how to write apparently. Has edges, which has, or which have, I think, orientation. So if you have a VW, it will never be equal to WV, right? So a directed graph could be something like this. So 1 goes to 2, for example. It will not be the same as, let me actually like put it right this. It will never be the same as this, okay? So this is what a directed graph is all about. Another example you might see in books, so you can have, for example, something similar to this. So 1, 2, 3. So for example, something like this, let's say, and then you could have 4, for instance, having something similar to this, and 3, for example, have something similar to this. So you could actually see a graph or get a graph that looks like this. Heck, you can actually even have a vertex that is actually floating without any connections. Okay. You can think of it like as an isolated city without roads connecting to it, let's say. Okay. All right. So moving along. So this is a directed graph. We have something which is called weighted graph. So a graph that is actually like right now has weight information. Says weighted graph. So by definition, it's a graph which includes weights or weight information on connecting edges. And it can be applied to directed and undirected graphs. Okay, so this is what it's all about, and it's obviously like you could have again a graph that looks similar to this, for instance, and you could, for instance, have a weight, so 2, 3, 5, and -3, for example. So you could have negatives or zeros, or let me put a 0 here so you can have all the scenarios. So you can have a 0 weight graphs and so on and so forth. All right. So this is what weighted graphs are. Now there are actually some special cases of graphs, but before actually I dived into that, before like I go into these like special kind of graphs, let's mention the complete graphs. So you have something which is called complete graphs. Okay, and the complete graphs, or complete graph, is are graphs where there is a unique edge connecting between every pair of nodes. Connecting every pair of nodes. So a complete, so we can call this a complete graph with n vertices. Oh, hang on. A complete graph with n vertices.
You're missing an E in complete.
Thanks. A complete graph with n vertices is denoted as the graph, or as a graph, or as graph Kn. Okay? And usually you have it something like this. A graph with one vertex is also valid, so it's a complete graph. This is K2. This is K3. And now this is K4. And by definition, there has to be an edge connecting every pair of vertices. Okay. Now, of course, K5 will have a little bit messier version, so I will just simply like discard it for now, but you get the idea. Okay. Now let's talk about the special kinds of graphs. So so you have something which is called a directed acyclic graph. So directed acyclic graph. And I'll just simply write there somewhere beside it special. A special kind of graph. Okay, it's a special case. And a directed acyclic graph means it's a graph that doesn't have any cycles. So let me write the definition here really quick. Simply are graphs, directed graphs. or digraphs. So directed graphs with no cycles in them. It's usually used to represent structures with dependencies. So let me write this down. So it's usually used to represent structures with dependencies. Now here's the interesting part. Git is in fact a directed acyclic graph. You cannot have a cycle in Git. So if you look at Git as a data structure, because it's actually relying on something, an inode. It relies on something called an inode data structure, and it's actually a graph. And if you look at Git, when we were doing visualization of Git, if you remember, it's actually a directed acyclic graph, practically speaking. So you could have a graph that looks like this. Let's see. I'm not allowed actually to have cycles, so it should be this, like so. Or actually the opposite way around, doesn't matter, because if you go here, so you go this direction and then you go this direction, you cannot go this direction because it's the opposite of that arrow, right? Yeah, so you need to be like careful when you draw these guys. But in any case, this kind of graph, for example, it cannot have a cycle. This also is a graph. It's directed acyclic graph. Okay, which actually brings us to the next special case of a graph, which is called which is actually like which trees are. So trees are actually a special case of graphs. So let me write this down like here, and let me put this annotation as well. So I'm going to call this special case, special. Actually, let me put this more clearly in case you guys forgotten. So let me special case, and let me write here special case. Just for reference, okay? So a tree is, well, which we're going to discuss later. Sorry. A tree is undirected, and sometimes, well, actually, usually it's undirected indeed. Undirected, connected acyclic graph. You cannot have a node that is floating somewhere without being like, you cannot have a tree that looks like this, for example. It's not possible. Okay, so that's a very important thing. So it's connected is a very good keyword here. Okay. A graph, that kind of a graph is it's this graph. So a tree is a graph. So it is a graph. It is a graph which is minimally connected. Which is also an important point, meaning that, so i.e., you could actually removing, so it's removing one edge so if you actually remove one edge, makes the graph disconnected. So this is a very important point. So as I already have mentioned, you could end up with something like this. So if you remove that edge, the graph became disconnected, which violates this, which violates this definition. So it doesn't become a tree, it becomes just a graph. You could actually have a graph, by the way, that looks like this. So this is your whole graph, okay? It's just a bunch of islands, right? And we're gonna discuss that in a minute. So yeah, couple more definitions here. It's also, so it's a minimally connected. Graph is also maximal without a cycle. So maximal means that you can log. So let me actually write this down so you guys don't forget this. It means that if you add one more edge, it will cause a cycle, practically speaking. So this is the these are the properties of a tree. So a graph, so it is a graph. So it's a maximal graph. Or maximally, oh, hang on. It's a, yeah, I will so call like, let me just reform my sentences correctly. So it's a maximally connected graph, meaning that if I adding an edge to the graph, will cause a cycle, which again will violate the definition. So oh, sorry about that. Okay. Let me write this as at least one edge. So if you add at least one edge to the graph, it will cause actually a cycle. Okay. This is generally what a tree is, and usually it looks something like this. Usually, like we show it in books or in lectures, that they'll get like trees, something like this. You could have a tree that looks like this, right? You could even have a tree that looks like this. It really depends on how you look at this. Sorry, would be like so. Okay, so you could actually have a tree that like just simply looks like that. Now you have something which is called a rooted tree. Okay, and a rooted tree is a tree with a designated or defined root. Okay, so for example, if you have a tree that looks like this, looks something like, let's say this, for instance. Okay, this is the root of the tree, for example, right? And if you have something like this, then this is the root of the tree. They call it the rooted tree because it has a designated, well-known root. Okay. All right, so this is like one of the special cases. The final special case, actually, no, this is actually the final special case. Yeah, I already covered directed acyclic graphs. So that's pretty much it, actually. Regarding the types of the trees which we might encounter. There are probably others, but these are the ones that are mostly popular and that we actually like. It's covered in most books and most textbooks and references. Okay, so let's see. Yeah, actually, like we can actually go without a break because it's the whole thing is not that very long. Uh, so we can actually like tank it through. Now let's talk about the data structures. So now this is all nice and dandy, but how can we keep this in? How can we keep track of this in computers, right? So if you would like to, actually, like if you look at navigation applications like Google Maps and others, you get interesting applications of graphs that you need, for example, to find paths, you need to find the shortest route and so on and so forth. But these stuff are being layered, right? Because I mean, obviously, I'm saying it's layered because I'm mentioning this right now because of the data structure which we need to discuss. So if you have a map of a city where you have so you have a city blocks, right? And you have like, so this is building, this is another building, and there's another building, and you need to navigate through a city. And this is like one of the easiest cases. Actually, even I think Mostar is quite interesting when it comes to this because the city is not flat. It actually has uphills and downhills. Which can actually add to the cost. It might add to the cost of how we actually reach to a certain point. So for example, if you have a hill and then you have another city here, and you have roads in between, like road over the hill, and then you have a highway that goes around. Right now you get interesting costs, like depending on how you would like to go from the city around the hill to the other town, for example, right? That if the town has this kind of grid layout, Manhattan blocks layout, right? So, and of course you have layers, so you don't have only buildings layer, and then you have the routes layer, you have also the geological map, geological information, and you have as well as Google Maps, since the cars are actually streaming, so the cars navigations, sometimes they stream back through the internet to Google. They immediately detect congestions in traffic. So this is another added layer of graphs. So you have like several graphs layered on top of each other in order for them to determine what is going to be the shortest and fastest route and so on and so forth. All this needs some management in the memory, and all this needs to be saved in some sort of a data structure. Now, there are many ways of doing this. I will discuss the popular ones. I will leave for you this. I will leave for you that you like go ahead and research more and read more in the books and research on the internet and see what other possible better data structures to present graphs. So yeah. So let's talk about this. So graphs, data structure, representation. I think there was a couple of Google talks about like how Google Map actually works. I can't really remember right now which ones. I mean, it's been a very long time since I looked at these stuff, so probably you can have a look at it on the internet and see what are the talks in there. It might actually widen your horizons a bit. So how can we save a graph in the memory? We have actually like a couple of types, like a couple of ways of doing this. You can actually save this. Actually, we have like 3, I think. So you have something which is called adjacency matrix. So let me write this down in yellow. So you have adjacency matrix, which is one way of saving data. And it's actually a very simple way. Oh, let me just. A very simple way of representing a graph. So a cell, because we are talking about the matrix, so a cell M, which is a matrix of I and J, right, represents edge with a certain weight, if you would like to have weights with a hang on. With a specific weight. Going from node I to node J. And this order is very important because if you reverse that order, that means that you have, if you would like to represent a directed graph, right now you have a specific order you need to take care of. Okay, so adjacency matrix, if you have, for example, something like unweighted graph, what you could do is, so for example, let me like show you this. So if you have nodes A, B, C, and D, and because it's a matrix, then it actually has to be as well from this side, A, B, C, and D. You could have, for example, like, is A connected to A? So no. What you could do is like have zeros and ones, right? And zeros and ones means that you could have a graph which is, for example, connected to so you have a vertex connected to another vertex, and the edge and all edges is like a weight of 1, which means it's like undirected. You don't care about like unweighted, so you don't care really about like what weight they are going to be. It's just simply like zeros and ones, and you don't care about the weights altogether. And I think if it is undirected, then you could just simply specify that on how you draw the graph. So you basically don't care about the order, practically speaking. So as you can see here, B and A and B are actually having like ones. But if it is directed graph, then you're going to have to draw it differently. Okay. So let me actually like show you this one. So you have like zeros and ones in order to denote like if the graph, so if the vertex is connected to another vertex, and that's it. Okay. Another way of doing this is that if you like to have weights, you could actually write in the weights. So for example, A has 0, 3, for B, 2 for C, and 9 for D, for instance, and then 2, 1, 3, and 6, 0, 2, let me just write this better, 2, 2, 5, 7, and for example, 1, 2, 3, and 0. So you could have, for example, something like that. And let me try to see if I can like adjust it a little bit so you guys can differentiate this. Okay, so you end up with a graph which is A, B, C, and D. And in order not just to waste too much time, you could actually so B is connected to B with 1, so it's something like this. So for example, A does not connected to A, but A is connected with B, so you have like 3 connected with C, so you have something like 2. So this is 3, and this is 2, and then A connected to D, which is having a 9 and an edge of 9, and so on and so forth. And right now you can just simply go ahead and have fun with this, right? So you can actually write it down like 2. B with B is 1 is already written there. B with C is 3, and B with D is 6, right? C doesn't have any connection to itself, nor D, so C is 0, 2 with B, which is going to be like this, which is going to be 2, 5 with C. Oh, C with C is actually connected to itself, sorry. C with C, forgot about that, so there we go. C is not connected to A, but A is connected to C, right? So there you go. So it's think of it like a one-way road or something. So this is 5. So if you would like, for example, to navigate from C to A, you need to go through B and then A, right? If you have like a city roads or something like that, and to D is 7, right? And D having with A is 1, and with B is 2. Right now it became a mess actually. With C is actually also 3. I will not write it down again. And with D is 0. So you have like a graph that looks like that approximately. Hopefully I didn't forget anything. So what are the pros and cons for using such a matrix, right? So what if I'm using this data structure, what are the pros and cons? So pros, it's a space efficient for representing dense graph. Or dense graphs. Okay, if you have graphs that has too many connections and stuff like that, it's really compressed way of writing such a like drawing such a very busy or very dense graph. Like dense means like too many things into it, right? I think dense can be translated as gouge. Edge weight lookup. How much time does it take me to get a weight of an edge is actually O of 1, right? And it is O of 1 because I just simply say give me that within that matrix, here's the node I and here's the node J, give me the weight, and it will immediately give you the weight, right? It's an like when you are accessing a certain element in an array by an index, right? So this is O of 1. And it's also very simple graph representation. It's not complex to implement, easy to it's actually easy to manage. You could like actually write an exporter and an importer of graphs by code, and it can be actually like a breeze to implement. What are the cons though? It requires O of V squared space. If you are having, as you can see here, we are having 4 vertices, yet I'm actually keeping track of 8, right? So that's the case here. Iterating over all edges takes as well O of V squared, right? So if I say give me every edge in the graph, it's a nested for loop. Not that efficient. With sparse graphs. If you have a graph that has very, very minimal connections, so it doesn't have like that many connections, so it has like a bunch of zeros in here, a majority of it is zeros, you are just wasting an allocated space. You're allocating a huge amount of space to keep track of a graph that doesn't have that many connections, right? So this is one of the problems with using adjacency matrix. Obviously, it will not matter if you are actually like using or doing something super simple, like this, for example. But if you are keeping track of something super large, like a map of a city, now it actually will start to matter, right? You have another one. You have another way of saving data of a matrix. So you can have, right now we have adjacency matrix. We have as well adjacency list. Okay. An adjacency list is just simply a way to represent a graph as a map from node to list of edges. So let me write this down. An adjacency list is a way to represent a graph as a map from nodes to list of edges. What does that mean, right? So if you have, for example, like you could think of it like like linked lists. I mean, do not confuse yourself. So if you're, for example, like having a list of, let's say we have A, B, C, and D, right? So you have a graph like A, B, C, and D. So you have these vertices, and what these vertices will contain, it will contain an array of every vertex it will point to. So for example, from A to B, wait a second. So from A to B is actually having a 3 there, right? So it's going to be like A is going to B and has a weight of 3, right? Hang on, let me actually write this a little bit better. So this is an array, and then you have B and 3, right? It's right now became a tuple, practically speaking. And then right now from A to C, and we have A to D, right? So from A to C with, I forgot the weight of it, so 2, for instance, right? And then you have to D with a weight of 9, right? And this is, for example, concludes A. I will fill in here arbitrarily stuff. So for example, you could have here, I don't know, A with 2, D with 3, for example, and end of the story, right? D, for example, could have nothing going out of it. So it doesn't go, like there are no arrows going out of it pointing somewhere else or connected to somewhere else. So everybody else is connecting to it except it. So yeah, you could also have something like an element of 1, so it can be connected to D, let's say, with a weight of 1, and that could be the only connection to it, right? So this is practically what a actually it could be like this. Okay, this what could be an adjacency list look like. So the question here is, what are the pros and cons, right? Let me just move this guy to the side right here. So. So, pros. Space efficient. For denser graphs. Iterating over all edges is also efficient. Or relatively more efficient. The cons, however, less space efficient for denser graphs, obviously. So less space efficient for denser graphs. Okay. Edge weight lookup is O of E, because if you would like to find an edge weight, for example, let's say A has, let's say 1,000 connections, right? Like the same thing when you guys are on Facebook and you have 1,000 friends, okay? If I would like to look up how frequently you are communicating with someone, I have to and if that someone is at the end of the list, for example, at this thousands elements, right? I'm gonna have to linearly search until the end, right? So if you think about it that way, unless of course you use some of the other searching techniques or maybe a different data structure instead of just a list, then maybe you can shorten that time. But if you are using just a simple list, adjacency list, like it's mentioned here, the lookup is that. So there could be other improvements. You can actually keep this, instead of a list, it can be a tree, let's say, and then right now you can actually like make this even more efficient. But there you go. A final bit which some people might find useless, but it's actually existing in real world. So Edgelist. And an edge list is simply, you are like, it's even simpler way to store if I know how to write today, to store a graph using, or represent actually, using an unordered list of U, V, and W, which is like the vertex 1, vertex 2, and the weight, right? It's not a tuple right now. It's like a triple, but it's a tuple, basically speaking. It's rarely used to due to its unstructured layout, or lack of structure, if you would like to say, call it that way. So practically speaking, you'd have like something like this: an array of A, B, and 2, then B, C of 4, then, for example, D connected to A by, I don't know, 0, for example, right? So you could have a list of this. And to be honest, it's like similar to, I don't know, it reminds me of polygons in graphics, because they are usually unordered graphs, like an ordered list of vertices. And then you could like loop over them to do certain interesting operations. Some people actually treat their problems like with some problems with graph theory in order to find, for example, connected polygons and disconnected polygons and so on and so forth. For example, finding if a certain like certain patches of polygons are connected or disconnected, detecting islands and stuff like that. I mean, it really depends on how you look at this problem, but Edgelist actually exists, but it's actually being rarely used in terms of like mapping or something like that, like maps and other different applications. I mean, it can be used in completely different applications than the ones which people are used to. So finally, in order to like, let's finalize this with common problems. Man. Common problems solved, or usually people are asking, they query the graph, so with graph theory. And please remember that this field actually existed way before computers were there. So you can find actually in history books a lot of interesting questions that has been asked, and currently we are using their answers that are again from the 1800s and 1700s and probably even earlier. You have a problem which is the shortest path problem, which I already have mentioned, right? So you would like to find shortest path between points or between 2 points, right? Excuse me. Algorithms used for that. So if you are actually faced with this at any point in time in your career, you could actually use BFS, which we're going to study. Not today, obviously. Dijkstra is also we're going to cover this semester. A star is not going to be covered. Heavily used in games. So if you see like an enemy or a game object like going from one point to another, navigating a map on its own, it's actually utilizing A star or one of its variations. Bellman. Billman-Ford. So these are two people, by the way, who written the paper. Also Floyd Marshall, also two people, so Floyd and Marshall. Algorithm for finding the shortest path. Another problem could be connectivity problem, which I think you guys have seen it with Goran regarding computer networks. Activity problems. How to detect if there are so it's basically speaking detects if there is a path between any two nodes. If there is a path between any given two nodes. So for example, if you have a graph that looks like this, or you have a graph that looks like, for example, like this, it will immediately detect if these guys are connected to these guys or not. Okay, so this is what connectivity problem is all about. Algorithms used. To solve this problem, you have something like you have DFS and BFS can solve this. Depth first search and breadth first search, which we're going to cover this semester. Also, you have something which is called a union find data structure. Okay. Another problem that actually can be that's actually which actually we'll discuss hopefully later when discussing DFS and BFS is traveling salesman problem. It's an NP hard problem, and let me just write BFS back. So given a list of cities and distances between them. So for example, you have like let's say Sarajevo, Mostar, Jablanica, Konjic, and then maybe Tuzla and I don't know, Vareš, and maybe other Travnik or whatever, right? So you're going to have like a list of cities like these, and then you would like to go through every. So if you are having a list of cities and distances between, and this is between every city, find the shortest path, shortest possible path to visit each city exactly once, and return to origin city. And traveling salesman is a very, very famous problem. And I think you could see this. I mean, if you are a delivery truck that's actually like going through multiple cities in a country to deliver stuff, you probably like that person, whoever is doing the delivery, is asking exactly the same question. How do I spend less fuel and time in order for me to deliver everything which I need to deliver and get back home, and while maximizing the profit, right? Because the more time you spend on the road, the more money you spend, and you would like to maximize the profit by reducing the costs to deliver goods to cities, right? Algorithms used. You have two persons, so Held and Karp. They published a paper on that talk. Any colony and sorry and any and colony optimizations algorithms, because there are many of them, and usually they are actually like heuristics, I think, heuristic algorithms. And they are, oh, sorry, not heuristic, approximating algorithms, actually, algorithms. So these are all approximations. Okay. The final one is going to be, which we're going to discuss in this semester as well, is minimal or minimum. Let me call it as it should be. So minimum spanning tree. So practically speaking, what a minimum spanning tree will give you, it will give you a it will give you given a graph, it will find a tree, practically speaking. So given, let me write it here to keep just to be consistent. So given a graph, it will find a tree that connects all vertices without any cycles, because it is a tree, right? Sorry, hang on, let me write this down better. Without any cycles and with the minimum cost. Okay, algorithms to solve this. Usually, actually, we use minimum spanning trees like to answer the questions, like to answer this question of traveling salesman. You have Kruskal. Kruskal's algorithm, Prim's algorithm. So it's actually Prim's and Borovka's, sorry, I made a mistake here. Borovka's algorithm are actually one of the most known algorithms to solve this problem. Okay, we're gonna study both of them in this semester. So yeah. This is actually pretty much it, which I wanted to cover for this part, for the graph theory bit. Like this is basically an introduction to what's actually going to come up next. So hopefully we actually next time we're going to be covering binary trees and binary search trees. Which are relying on this fact, relying on the fact that we already know what graphs are and how we store them and what kind of problems we are trying to solve with graph theory in general. So let me stop recording.